my pen. Whoa, check that out. It's stuck in draw mode. Stop it. So inverse trigonometric functions, we're going to go back to the basics about trig first. So we took a look at the graph of the inverse sine. I want to go back to the unit circle for a moment. To our basic definition of what a trig function is. All right, so back to basics here. So on this unit circle, that's 1 up there, -1, -1, 1. I have an angle for this radius right here, and my radius is 1. On the unit circle, I have some point xy, and I know that on this circle, y is equal to the sine of theta. So I just want to remind you of what the original purpose of the sine is with respect to the unit circle. What the sine does is it converts angles into y values on the unit circle. Now, similarly, the x value does something similar, right? The x is the cosine. So x equals the cosine of the angle. And what does the cosine function do in this fundamental way? It converts angles into x values on the unit circle. So we always have that interpretation of how the sine and cosine behave. Oops. Angles. And then one more, let's do the tangent. Tangent is the slope, right? It is m slope y over x on the unit circle. And so what does tangent do? It converts angles into slopes on the unit circle. Right, circle of radius 1. Now consider what the inverse trig functions do. So each of these has an inverse. So for example, the inverse sine is often called the arcsine. So now we have this new function like y equals sine inverse. I'm going to just put an x in there, which we often write as the arcsine. Some computer systems, it would be called the A sine. Depends on your calculator. Sometimes it has the inverse symbol. Or we have the cosine inverse, which is also known as the arc cosine. And then we have the inverse tangent, which is also known as the arc tangent. So if the original functions take angles and convert to either y values, x values, or slopes, the inverse functions take y values, x values, or slopes and convert to angles. So each of these inverse functions outputs an angle. Now on the unit circle in particular, I'll zoom out of the way, there you go. The angle is the same as the arc length. So that right there, that arc is theta. So theta radians, that's supposed to be a theta there. Let's try that again. Theta radians on the unit circle leads to an arc length that is also theta. So if the radius was measured in centimeters, then this arc would be whatever theta is, but centimeters instead of radians. So another way to think about these inverse functions is they output angles, and on the unit circle, angles are arcs. So also arc lengths on the unit circle. Hence the name arcsine, arccosine, arctangent, and so on. So output is an angle or an arc. I tend to think about it as an angle because that's more general. It doesn't matter whether we're talking about a unit circle or a bigger circle or just a triangle. Okay, so let's look at an example of this. Use of an inverse trig function. All right, so let's suppose I have a triangle that looks like this. And I know that it is a right triangle. And the height of this right triangle is 4, and the base of the right triangle is 3. I would like to know what is the angle of such a right triangle. Now you might recognize this as a 3, 4, 5 right triangle. The hypotenuse would have to be 5, which is cool, but I'm just going to worry about these right here. Now, next I want to think about what trig function relates the height to the base. So if I'm thinking like circle-wise, I could say, well, that's the y value, and this is the x value. If I'm thinking right triangle trig, then this side over here is opposite the angle, and this side right here is adjacent. And then I'm thinking, okay, which trig function deals with opposite and adjacent? Well, that reminds me of the tangent of theta is the opposite side over the adjacent side, or y over x if I'm talking about a circle. So then for this triangle here, I know that the tangent of theta has to be equal to 4 over 3. And I can find the angle by just solving this by applying the arc tangent. To solve for the angle. So these inverse functions allow me to solve, just like a square root helps me solve a square, for example, or a cube helps me solve for a cube root inverse function. So 2 ways to think about it. One is I can just jump to the conclusion that theta has to be the arctan of 4/3. If I think about when we're solving equations with square roots, we usually write the square root on both sides, and I could do that too. That's kind of an extra step in the middle. So starting with the tangent of theta equals 4/3, I could then apply the arctan, which is often called the tan inverse, to both sides, like that. A function and its inverse cancel, leaving just theta. So the answer has to be whatever the tan inverse or arctan of 4/3 is. So then I have to go over a calculator and ask, pay attention to the mode of the calculator. Desmos, my recollection, is in, let's see, the settings button is hiding behind zoom there, is in radian mode, which is generally what we want. So now if I ask this, okay, what is the arctan of 4/3, it's going to give me a radian angle of 0.9273 if I went to 4 decimal places. .9273. So according to Desmos, that angle is approximately 0.9273 radians. If you wanted the answer in degrees instead, you could convert. That would be one option, or just change the mode of your calculator. So I'm just going to double check that both ways. If I wanted this in degrees, then I would convert by recognizing radians goes in the bottom for my conversion, degrees in the top. 180 degrees is the same as pi, or you could do 362 pi. So if I take this number and multiply by 180, divide by pi, that should give me the degree version of that angle. So we'll check that in 2 different ways. So I'm going to take that previous number, the arctan of 4/3, I'm going to multiply it by 180 over pi. And I get about 53 degrees. And if I look at my picture, which was reasonably accurate, yeah, I'll take that. It's a little bigger than 45 degrees. So I think that's about 53 degrees, approximately 53 degrees. And let's check on another calculator for fun. So I could just switch the mode here. Let's see, that would be the monkey wrench, and then switch to degrees, and it recalculates everything, making this number worthless. But I can see that 53 degrees when I switch the mode. So again, pay attention to your mode when you're playing with trig functions. Notice what happened to the graphs here when I switched. Whoa, that's some crazy crap. Here, look at that. So again, trig functions are meant to be graphed in radians. And if I switch degrees to radians, then weird stuff happens with the graph because, again, 1 radian is more like 50 something degrees, 57, I think, ish degrees. So keep that in mind.